Okay, so let's go ahead and do office hours. We're working on homework 1, so the things that we could be asking questions about today are we could be looking at homework 1, since we've got that quiz later today. Just problems 1 through 21. We haven't gotten to the atoms and things like that. We could be looking at the absorption lab, the prep activities, or if you're getting ahead, we can also look at some of the post-lab questions for the lab. But from my understanding, most of you want to ask homework questions to start. What homework questions do we have? Let's just start a list.
21.
19, 21.
20.
20.
Well, I don't really have questions, but I just want to know like the answers.
I don't have the answers.
Oh, okay.
Since the
Just to know if I'm doing
with-
the work correctly.
yeah, we can look at them. If there's some in particular that you're worried about, we can look at those specific ones, or I can just look over it and see if it looks like you have the correct process.
Oh, okay.
Because that's the more important thing, is having the correct process. And you can also check with each other.
Okay, awesome. Is that what you think? Yeah. Okay.
Probably right. Oh, we could also talk about the unit conversion quiz if anyone had questions about that thing online.
15.
15. Which one is 15?
It's the one with the Jekyll and Hyde.
Good. I was hoping someone would ask that one.
I don't. I have 71.2.
I really like that one. Let's do that one first. Is it okay if we do that one
Yeah,
first?
I didn't know how to do it.
Okay. So do me a favor. If you've got the problem, go ahead and read it out to me.
I have it. On a new temperature scale, the Jekyll scale, water freezes at 17 degrees J and boils at 97 degrees Jekyll.
Okay.
And the Hyde scale, water freezes at 0 degrees and boils at 12 degrees.
Okay.
And we want to use that information to convert the boiling point of methyl, which is 8.13 degrees Hyde, and to the Jekyll and Celsius scale. Convert that to the Jekyll.
Okay, so we've got some interesting information here. And so what I did was, while you were reading the problem, I kind of wrote down the technical information, right? This is what the question is really asking. Can we take the 8.13 highs and convert it? It doesn't matter what material it was, right? It gives us a specific material, but that doesn't really matter. All that matters is we've got some measurement on the Hyde scale, and we want to convert it to Jekylls and Celsius. Right? And then we have this other information about these new scales where we've got the freezing point. Is there an E on the end of freeze?
Yeah. Yeah.
And boil. We got freeze, we got boil. Right? And at this point, we don't have enough information to do anything. We need something else. What other information do we have? And I like to break this down into kind of 2 modes of thinking. We've got explicit information, right? This information is explicitly given to us, right? It's given, the numbers are given to us. Then we also have the implicit information. That is to say, the information that the problem assumes we already know.
Which is that degree Celsius freezes and boils at 0 out of 100.
Yeah. So this extra bit of information, that's implicit. Like the problem assumes you already know that. You can't do the problem without that. So as we start, and again, one of the main things we do in Chem 124 is we learn how to analyze problems. We learn how to break down problems. So we've got our explicit information, we've got what the question is actually asking, and we've got our implicit information. Now we have to find some way to relate them. So let's do the easy thing first. Let's say I wanted to relate Hydes to Celsius.
I did 8.13 over 12, and then I just found the
Yeah,
ratio.
right. There's
That's
a
what
simple
I
way to do this first one. There's a pretty simple way to do it, right? We can just say 8.13. Wait, I'm messing this up. 8.13 Hydes is question mark Celsius as 12 Hydes is 100 Celsius, right? Now, why do we get to do that?
It's a ratio.
Yeah, right. And so it's going to be more complicated when we move to the Jekyll scale. And so we're going to do something a little bit more complicated, but a little more generic to see why this works. So essentially, we're trying to relate these two things to each other. And whenever we're trying to, and we're essentially trying to map one thing onto another thing. Does that give you any ideas of what we might want to draw?
An equation.
Equation of a line. More importantly, we can draw an axis system, right? And we want to find Celsius, so I'll put Celsius on the x-axis, I'll put Hydes on the y-axis, but we could do either way. And this one's relatively easy because they both have the same freezing point. Then up here at 100 Celsius and 12 Hydes, we've got another point. This gives us, well, that's almost a line through the point. Pretend like let's just, close enough. This gives us a line. When we write the equation for this line, we're going to have Hydes is equal to, so that's our y equals, let's write this down. Right? Equation for a line. That's going to be really useful for this problem, for the lab that we're doing today, and later on in class. Like the equation for a line is fantastic. The slope for this is the rise over run, so that's going to be 100 over 12. Our Celsius is going to be our x-axis, and then because the intercept is 0, we get a plus 0. Oh, you are so right. I was like, man, I made a mistake someplace because that should match. Rise is 12. Run is 100. So you notice, because of this simple situation, it really is just a ratio because we've got no y-intercept. It's just the slope. But the funny thing is, whenever we have a ratio, we can actually think of it as a slope, relating two things to each other. All of the conversion properties we've been learning, we can all think of those as plotting two things against each other. So now we can very easily convert Hydes to Celsius, Celsius to Hydes. The next thing we need to do is come with a way that we can relate the other two. So I'm going to give you all a minute. If you didn't do this one, or if you did, go ahead and make a relationship between Jekylls and Hydes. Let's come up with an equation that relates those two. I'm going to put Hydes on the y-axis. Again, I should put Hydes on the x-axis, huh? That's going to be easy. Let's put Hydes on the x-axis. Jekylls on the y-axis. I'll give you a minute to kind of, if you're watching at home, go ahead and try this at home too.
While they're doing it, can I ask you a quick question about number 9? So it asks for the one with the best average, and they have the same average, so I just put both of them, right? And then this one asks for the standard deviation, and that's. And obviously, that's this one. Okay.
For the two ratios that we have set equal each other for Hydes and Celsius, could we just like multiply across and then solve it too?
Yeah, you notice if you multiply across, you get this equation. Right, so if you bring the Celsius over there, you get 12 over 100 times 50 Celsius gives you Hydes. So that does totally work. Right, and the nice thing about having that simple case is it gives us a way to see, like, your intuition was correct, right? Just going with a ratio works. But the reason that worked so easily was because they had the same freezing point. So when they have a different freezing point, that gets a little more tricky. So let's go ahead and start looking at this. If I look at the Hyde scale, I'm going to freeze here at 0. And when I'm at 0 Hydes, I'm going to be at 17 Jekylls. Then, when I get to 12 Hydes, there's a little bit more space. I'm going to be up here at 97 jackals. So what I have here is my jackals equals y equals m. That's going to be rise over run. I can do this right this time. 80. Over 12 hides plus b. Notice in this case, b is not 0. It's 17. We could calculate that if we set it up a different way, if we set it up the opposite direction or anything like that. We could calculate it by simply plugging in 0 hides into this equation is 17 jackals. So plug in a 0 there and a 17 there and solve. But when we solve, we're going to get that this is 17 degrees. Now, I can plug in any unit of hides and get my jackals. And notice we've got this correction factor that we also have to take into account. I don't need to put degrees there. It's just a number. But again, you notice that this is just a y equals mx plus b. We've used just plotting the two things against each other in this linear fashion to come up with a relationship between the jackals and the hides. Have you ever looked at the equation 9/5 Celsius plus 32 and wondered like why does that why? It's this. We'll do that in class today as well because I love that example for leading into the lab we're doing today of how do we actually come up with the equation that relates Fahrenheit to Celsius. We have some, and notice the reason that this works is because we have some physical information about how these two systems relate to each other, right? We have the freezing point of water and we have the boiling point of water on that particular scale. So we could do the same thing if we wanted to relate Celsius to Fahrenheit, which is 32 degrees boiling to 32 degrees freezing. I wrote it in the freezing column, I wrote the temperature for freezing, and I said the wrong word. And then 212 degrees for boiling. And now we can make a relationship between these two, and you'll get the equation on your equation sheet.
You guys have an answer for it? For jackals. What did you get for jackals?
I don't think they're there yet.
Oh,
Let me see. But this is the process you did?
I said it differently.
Oh, did you just set up different ratios?
I did.
I got an answer, but I don't know if it's
I
right.
got 71.2 jackals and then I got
Well, we just use that.
67.8 Celsius.
Okay.
But I think I might have done it wrong because
How did you do it?
I did it. I did it really dumb. I did something.
Oh, you got it looks like you solved for the slope. You got 4/5 for the slope.
That was for relating jackals to Celsius, and then I got the Celsius number.
Okay.
I did it really dumb.
No.
The 2 zeros threw me off, so I was like, I went from like getting one answer to converting it to the next.
Gotcha. So you went Celsius to jackals, jackals to
Yeah.
hides. That should still completely work. It
Yeah.
is a little more complicated.
Yeah.
But it should still completely work.
I got 71.2.
Yeah.
Okay. There
The
you
way
go.
that I did it at first just works for that. I just did
Just this?
pretty much.
Yeah. That should also work.
Yeah, I just did 8.13 divided by 12, and then just use that decimal times
100.
80, or for jackals, yeah, because
Oh,
the
yeah,
range
yeah.
is 80, and so you get,
In my head,
Check
it
something
makes
real
sense.
quick.
Did you guys get 16? It's like really simple. I just want to make sure I got it right.
y-axis is temperature, the x-axis is time, and the slope would be related to the relationship between time and temperature.
Yeah, or K, right?
Is that the planetary temperature one? Yep. Should we go on to, so that was number 15? That was 15. Done with that. Let's go ahead and look at 19, 20, 21, and hopefully we won't have to do all of them. Hopefully we can just do one of them and it will make sense for the rest. Was there another question you had?
No.
Okay. I saw the confused look on your face and I got worried.
I was just wondering, because 20 is a definition problem.
Oh, is it?
Yeah.
Still, it's a new definition problem. So. What's problem 19? Someone else want to read?
It's really short. It's not like calculations. It's just explanation. But I don't.
just have them printed out.
Oh, okay. Yeah.
And it just says, if the stock solution in all the previous problems is a red dye that absorbs light, how would the peak height qualitatively compare between all four cases? And the question 17 and 18 are part of this one.
Yeah. So we've got 4 solutions. Each one has a different concentration, right? How does concentration relate to absorption?
Directly red.
So this is pretty much like a constant. Absorption and concentration are directly related. So all we have to say is, as concentration goes down, absorbance goes down.
Yeah.
That's it.
Yeah.
Right? It's just that direct relationship, realizing that there's this equation is representing the physical world. It's actually not, you know, in our math classes sometimes, in other classes, we come up with these equations and they're just equations. In chemistry, every equation we write down is trying to represent some physical phenomena that we can observe. And sometimes it's things that are intuitive to some degree. We know that as we add more water to stuff, the color gets lighter. Explicitly, in terms of our chemistry class, we would say as the concentration decreases, the absorbance decreases. It's a way to explain Kool-Aid getting watery. 20 or 21? What's 20 is the definition of the molar absorptivity.
Yeah.
So the main thing to remember for molar absorptivity, we'll just do this one really quick. The main thing to remember for molar absorptivity is that it depends on the identity of the material, and it depends on the wavelength of observation. I'm answering the right question, right?
Yeah.
Yeah. Okay. So it depends on these two things. So that is to say, as long as it's the same material, same chemical compound, and we're observing at the same wavelength, epsilon is the same. If we change the chemical compound, we need a new epsilon. If we have the same material, but we change the wavelength, we need a new epsilon. So if either one of these things changes, we need a new epsilon for that observation. As long as we keep them the same. And we saw this in lab on Wednesday? We saw this in lab on Wednesday, where we looked at blue, we looked at red, and then we looked at what happens when we mix blue and red. It looks purple to us, but the blue molecules are still blue molecules, and we kept the same wavelength of observation. And the red molecules were still red molecules, and we kept the same wavelength of observation. So we could use the same epsilon in those cases. Let's go ahead and look at problem 21 to see kind of how that gets wrought out in a problem.
So yeah, 21 is like kind of related to like the report form that we did on Wednesday.
Uh-huh.
I'm just kind of confused about the conversion from mu molars to moles over liters, so that we can get to the correct units of molar absorptivity.
Answers for sure.
I didn't get any.
So mu is the Greek letter, it's the Greek letter. It represents the prefix micro.
Mhm.
So like micromolar is 1 times 10 to the minus 6. That's one of the prefixes we should remember.
Okay.
So there were a few we should remember. Let's go ahead and write those out. I'll write really silly things. Molarity is just 1. Centimolar, no one ever uses centimolar, but just so we have all the prefixes. The C prefix is 1 times 10 to the minus 2. Millimolar we do actually use sometimes. That's 1 times 10 to the minus 3. Then we have micromolar, 1 times 10 to the minus 6. And then we don't often get to the nanomolar scale, but that would be 1 times 10 to the minus 9.
There's
And-
like, oh sorry.
Okay, I was going to say, and you have to be careful when you're looking at plots, Beer's law plots, you know, these things that are like concentration versus absorbance. You have to be careful because sometimes they report the concentration in micromolar, sometimes they report the concentration in molarity, and if you don't notice that, you're off by a factor of 1 million. It's a little bit significant. So make sure you're paying attention to what units that whoever's reporting the graph you're looking at, pay attention to the units on the graph. And what were you gonna say? Sorry.
Could you? There's 4 parts for 21, but I like did them all. I just struggled with B.
Sure.
You just do part B.
Yeah, can you remind me of what part A is though?
Part A was the stock solution has an absorbance of 0.742 at the wavelength of 430 nanometers. What is the molar absorptivity of this wavelength? And then B.
And we have the concentration of the stock solution?
Yeah. Oh, sorry. 35 UM. What's the one?
Micromolar. Okay, so we want to find epsilon. Again, notice I'm breaking down the question, writing down the technical information, writing down the thing that we need to find. The implied information, the implicit information, this is all explicit.
Yeah. 1 centimeter per length.
Oh, I forgot about that one. And the other thing that's implied? Beer's law.
Oh.
Right? The actual fact that it's A equals epsilon LC.
Mhm.
So we can put all of this together. We know the absorbance, 0.742. We don't know epsilon. We know that L is 1. We know the C is 35. And I can leave it as 35 and report this in micromolar, or I can do 35 times 10 to the minus 6 and report it in molarity. I'd rather report it in molarity, personally. And then it's just algebra. Or
Wouldn't it
not
be-
even algebra, it's arithmetic.
So you should times 10 to the minus 6 to get to
Yeah.
change it. Okay, that's pretty simple.
Why did they?
You could also write this as 3.5 times 10 to the minus 5.
Yeah.
But same.
3.5. I wrote it
Negative.
as 3.5 times 10 to the 7, and I don't know why.
Ooh, if you put this as positive 6 and then moved your, no, that doesn't make sense to
No, it
me.
doesn't make sense at all.
No, I don't know why you did that.
Maybe you should write the number.
I think I just got the conversion wrong.
That's possible. If you did 3.5 times 10 to the positive, no,
No, it doesn't
no,
work at
I
all.
know. I cannot think of a way.
I looked at the conversions. I didn't know the conversion for it, and I got 10 to the 7 to get from micromoles.
Oh, so you have to be careful
Yeah.
if you're going from if you're going from molarity to micromoles, it's times 10 to the 6.
Yeah.
If you're going from moles to micromoles, it's times 10 to the minus 6.
Yeah.
So that directionality of whether you're going from the big thing to the smaller thing or the smaller thing to the big thing probably is what.
Yeah.
And that's the most common mistake. So
Yeah.
let's do a quick aside just to make sure we don't mess this up. So if we've got 3.5 times 10, oops. We've got 35 micromolar. You know, I'm already jumping, I'm doing the conversion in my head already. So let's do it explicitly. We got 35 micromolar. We're going to say we've got 1 mole has 1 times 10 to the 6 micromoles.
Yeah.
Right? And the thing that a lot of people mess up is they see this and they put it on top instead of bottom.
Yeah, it was 3 in the morning and I did it in my head, I think. It was like,
So the easy thing to do is write down 35, and that lowercase mu is just times 10 to the minus 6. You can do the same thing with like, so if I give you 430 nanometers, and I say, what is that in meters? Just turn that n into 430 times 10 to the minus 9 meters. Done. Right? We don't need, like, it's nice if you move the decimal place and say 4.3 times 10 to the minus 7 meters, but like one step at a time.
Yeah.
Okay.
I still couldn't figure out part B. for this
So,
one.
one thing I want to point out before we move to part B.
Yes.
Wavelength doesn't matter as long as it doesn't change.
Yeah.
Right? So as long as we're using the same wavelength, we're good. Let's go ahead and go to part B.
Yeah, it's just the language that messed me up. Because
Okay.
the stock solution is diluted by a factor of 10.
Yeah.
Okay.
I didn't understand that. Can we keep going?
No, let's get
Okay,
that.
okay.
So if we dilute by a factor of 10, what's the concentration?
Like, I don't
Maybe
know.
it's less by, like the concentration goes down by a factor of 10.
So it would just be 25
So would it be
micro.
Not 25. Oh, not down by a factor of 10 is divide by 10, not subtract 10.
so would it be
Okay.
35 times 10 to the minus 7?
Yeah, or 3.5 micromolar. That's it. Right? So imagine you've got, you know, like 1 milliliter of stock solution, you add 9 milliliters of water to it, so now you're at 10 times more solution without increasing your molecules. You're at 1/10 of the concentration.
Correct. Yeah.
If I give you $1 and then I increase your wealth by a factor of 100, how much more money am I giving you? 100. Right? So that's an increase. This is decreasing because it's dilution. Just divide by 10.
Right. Do we have time left? Sorry.
Yeah, we got a ton of time left.
For path length, we just always use 1 centimeter.
Unless it explicitly says otherwise, Beer's law path length is always 1 centimeter.
So the wavelength, like in the report form, the wavelength max that we found is not the path length.
Correct. Wavelength max is the wavelength of observation, right? That's where you're making your observation. It was the top of the peak in each one.
Do we get a calculator on the homework quiz?
Yeah, you get a calculator. You just have to
Scientific, we use a scientific.
We don't get to use our homework, right?
No.
Okay. So, yeah, I know, but like, I just like homework quiz. I really do not understand the prep activity at all.
The what?
The prep activity, I think it's pretty much all wrong.
Oh, the first one?
Would you like to take a look at the prep
I would
activity?
love to take a look at the prep activity if you guys
Yeah,
are
The
done with
first one or
it.
second one?
The first one.
And so should we have Excel, like downloaded? Should we just get that?
Yeah.
Okay.
If you go to
It's
your Poly.
free.
Yeah, it's you go to your email and calendar, and then it redirects you, and you can.
It's not Excel online? Because Excel online, you can't do everything it's asking.
Right. So
Yeah, I
Excel
tried-
Online misses a bunch of features, but as a Cal Poly student, you have free access to Excel
So I should
and
cancel
all of the
my
Microsoft, all of the Microsoft suite.
I just uploaded it.
It might be
It's
a
free
trap.
for a reason.
Yeah.
All I'm saying. I was using it last night to try and do the graph of like the concentration versus absorbance for activity 2, and it like has so much lag. It's ridiculous.
Wait,
I just did it on my
Excel Online.
Excel, yeah. I don't have
I
Excel,
created the
but-
graph on my graphing calculator and that's it. Because I knew how to do that from stats in high school and then it. There's specific
Don't like
questions about Excel.
Excel.
What do we want to look at?
Just like I really like I didn't understand the like way the simulator would, like, for the color part. I didn't where to find it. So I guessed.
Huh. Okay.
Like it was like a little color
Yeah.
thing.
Yeah.
And then
So the way that the simulator works
Yeah.
is you've got this like flashlight that's
Yeah.
like shining light out.
Yeah.
You've got your sample, and then you've got your detector here that's got like a wire attached to it. The
Mhm.
wire has like a reading on it.
Yes.
And then over here, you've got this slider. Where you can change the color of the light. And what you're supposed to do is you're supposed to slide this through all of the colors and see how the reading changes.
Oh my god. Okay.
Yeah.
Did not do that. Wait, and then when you get to the like with the max point from there,
Mhm.
that's the color you record.
Mhm.
Okay. And then that's the color that's
Oh.
absorbed.
Right. Well, so this thing has an option where you
For
can look at
transmittance
percent
versus-
transmittance,
yeah.
or you can look at absorbance.
Absorbance.
We want to look at
Do you
absorbance.
only
Oh, look at absorbance. Okay.
do you only write down like one for each, like the one that's the most?
Some have two
transmitted?
peaks. So if you see two distinct
Oh, okay.
peaks, you can
So
write
it's not
down like
just all
two
of them
distinct
that are-
peaks.
Kind of that are like going through. Okay. I just wrote down like everything that had a high percentage of transmittance. But we just do the peaks. Right?
Yeah, you would want high absorbance or low transmittance is really what we're looking
Yeah.
for. Otherwise, you're going to write down a whole lot of things.
Yeah, I was just writing down like all the ones that like looked like they were going through like the most.
Yeah.
But we just do the peaks.
Wait, can I ask you if the answer for something is correct?
Sure.
Like,
Yeah,
hold on.
yeah,
Okay.
yeah.
For the third one, is it because there's like very little purple light, but there's a lot of red and blue light?
I don't think so.
Okay.
I think there's very little purple light, but there is yellow and green and a little orange. So you have all these
Okay.
other things that give the appearance of purple, right? And this is what we're really getting at with this, is breaking down this whole phenomena into 3 steps. We've got step 1 is right, so this color slider, the color of the light, this is changing what light is produced. This is, in the spectrometers we use, it has a diffraction grating. It has this, essentially a prism that it rotates back and forth to make it so different wavelengths of light are hitting the material. Thing number 2. The light interacts with the material, right? So that's the interaction that we really care about. And then thing number 3 is, I call it stray. So then the stray light makes it to our eye, whether that stray light is light that wasn't absorbed or light that was reflected, however it gets from the material to our eye. You also have phosphorescent and luminescent things that could be producing their own light. However the light gets to our eye, it hits our eye and is interpreted. And I call these 2 things very different. Like, this is where we're worried about absorption. And if I could spell. This is what I call the appearance of the color, right? So the material interacting with light is what we typically care about, right? The way that our brain takes in light and interprets it is pretty darn complicated. We've got rods, we've got cones, we've got 3 different kinds of cones. Those cones send signal to our brain. Our brain then kind of converts that into spatial color information. In order to remove that idea of how we interpret color, the fact that this appears black versus this appears green, the way that we separate those 2 is by using a spectrometer, so we can just look at how the light is interacting with the material. So the spectrometers we use in class eliminate step 3 and just do this with a spectrometer. And the thing that this little online simulation is trying to get at is this extra complication, right? You look at a solution, I can't remember, I think it's the third solution is a cobalt chloride solution, and it's got this weird, like, I won't say it's ugly, but it's got this ugly salmon color associated with it. And when you go through the slider and you look at what wavelengths of light are absorbed, it's completely independent of the way that, well, it's not completely independent of the way it appears to us, but the way it appears to us is very different from the colors that are actually absorbed. Because you're dealing with either light that's not being absorbed, like red light getting through, or complementary colors being absorbed, which all messes with the way that our brain interprets it and the way that that color appears to us. And then, you know, you got black is like nothing's reflected. It's the opposite of color getting to your eye. But somehow our brain can interpret it. It can spatially interpret it, right? So when you look around the room, you can see like dozens of colors, dozens of shapes all at once. But our brain can actually make that spatial distinction. And then it can also, at the same time, it can take the weird squiggles I put on the board and translate it to meaning. All at the same time. So it's a little bit much. So we just try to take the brain out of it. We use a computer for the quote-unquote brain. We use a light diode for the light source and a detecting diode for the detector, and just try to eliminate that human aspect of interpretation. Does that help?
Yes.
Cool.
It helps. I mostly just like, I understand the concepts, I just like could not figure out how to
So
work this thing.
for that light purple solution, so it was the potassium permanganate.
Yeah.
KMnO4. It appears, but it's not really purple if you look at it. And keep in mind, it's a computer simulation kind of showing you a color. It's kind of like a pinkish purple to me. Right? So then we have to think, okay, if it appears pinkish purple, what's the absorbance? And what we can do is we can do this backwards map of like our logic of, okay, if it appears this color, it must have these absorbance peaks. But really the better way to do it is get the absorbance peaks and use that physical information about the material to explain why it appears a certain way to us.
Wouldn't it be like yellow and green absorbance?
Probably, yeah. Right, so yellow absorbance would give us a purple color.
Yeah.
And then green absorbance would give a reddish color. Mix those two together, we get pinkish purple. I think if we look at it, it also absorbs into the blue a little bit, which adds a little bit of an orange hue to it. But again, it's better to go from the physical information about the material and then explain why our brain interprets it, rather than trying to do it the other way. Because there's other ways that our brain will think pinkish purple. There's a lot of different absorption phenomena that could give rise to the same appearance. But we want to know how it's actually interacting with the light. Did anyone do the second prep activity?
I started it.
Do we want to talk about it? Wait, do you have a different question?
No,
Second prep activity? Second prep activity? Second prep activity, okay. Let's take a look at the second prep activity. Can someone remind me what the second prep activity is? Because I think I'm thinking of the prep activity for the next one.
It's this, if you want to.
Yellow dye, right, okay, cool.
The Excel with the graph.
I was thinking of the wrong thing. I'm thinking a lab ahead already. I'm already thinking of the emissions labs prep activity, which you all have those done? Okay, sorry.
Good one.
Let's just look at this prep activity that we're actually supposed to have. Prep activity 2. We're making a relationships. This, for those of you that were here just a moment ago, this goes back to the Jekyll-Hyde scale and how we relate to things. So, we want to create a relationship between absorbance and concentration. So we're going to make a plot of absorbance versus concentration. And I picked absorbance on the y-axis because I already know where I want this to go. I know Beer's law. And I know the equation for a line. I'll put a little something extra on here. If there's no material in your water, how much light does it absorb?
There's no material?
If there's nothing but water in there. Nothing. Right? So our intercept, our plus b, happens to be 0 in this case. In this particular case. But we can draw this connection and say, if my x-axis is concentration and my y-axis is absorbance, my slope is my molar absorptivity. So now we can go ahead and we can make our plot. We've got an absorbance, and we've got some concentration associated with it, and we've got another absorbance, another concentration, another absorbance, another, and another, and another, and another, and another, and another, and another, right? And then we can make some line through it. Let's try that again. A little bit better. And we've got kind of two options for how we approach this, and I'm probably going to talk about this in class today as well. Right? You could, for each data point, take absorbance divided by concentration times L, where we know L is equal to 1, equals epsilon. And we can calculate that 1, 2, 3, 4, 5, 6, 7, 8 times, right? I think there's 8 data points. You can calculate that 8 times and then take the average of those 8. And you're doing essentially the simplest statistics possible on your data. What we do when we plot this in Excel and ask Excel to do a linear fit is we are doing essentially a more complicated statistical analysis of our data to get the best fit, to get the least spread, get the equation that is the least distance away from every data point. And you should get some equation spit out. When you put this in, you go and you do the linear plot. You get the equation for it. Make sure you change the units so you can actually read the equation. Are you all comfortable with Excel? Did you watch the Excel tutorial video? Because that helps. The Excel tutorial video actually does the prep activity for the next lab.
Okay.
So, like step by step. But for this one, after you put your data in, you do a linear fit and tell it to show the equation, and you should get some numerical values. Do you have that?
I have that.
What'd you get?
So I put my it's r squared, right? R squared value?
No.
Oh, the equation.
The equation.
I got 0.0247x plus 0.029.
Did you plot your concentration in micromolar?
I just took it right from the data set. I didn't.
Is the data set in micromolar?
I don't have the data set on me.
Yeah, the concentration.
Yeah.
So the reason I knew that happened is because if you remember from part 1 of the lab, notice the way this is set up. What's this slope going to be?
The absorbance.
Not the absorbance.
Molar absorptivity.
Molar absorptivity, right? And if we remember from part 1 of the lab, we expect molar absorptivity to be on the order of tens of thousands to hundreds of thousands, right? So when I look at this, I'm like, oh, you're off by a factor of 1,000,000.
Right.
Which is because this concentration was in micromolar. So that's where your factor of 1,000,000 is. It's fine as long as you're aware of that.
Got it.
And it's actually kind of nice because if you leave this in micromolar, when you plug in your absorbance and calculate your concentration will also be in micromolar.
Okay. Got it.
But you have to be aware of that.
Okay.
If you reported that concentration in molarity, you'd be wrong. So make sure you're paying attention to your units. And if the problem explicitly asks for epsilon with units of molarity,
Yeah.
you would also be wrong. You'd be off by a factor of 1 million.
Yeah, got it.
Question.
I'm just confused on like what to plot, cause
Let's take a look.
okay, so I know that there's like the volume, it gives you the volume, like, and it gives the concentration, so how do you plot?
So you also, right. So this is, there's an extra step that I forgot about, because the data that's given to you is this data, right? It's the volume of the stock, the volume total, and the absorbance, right? So what's the first data point? Let's just get the first line of information.
Volume stock is 50,
Let's do the second one. 50 is good. Well, then let's do this one. Let's do 50.
and then
Let's do the first two.
and the absorption is 1.266.
What's the second one?
40, 50, and 1.015.
So first thing that we notice, if my total volume is the same volume as my stock solution, let's get a concentration here. Am I diluting at all? So what's my concentration? Oh, 100% of the original. So what was the original concentration?
54.5.
So this first one is still going to be 54.5. We'll just put the concentration here in micromolar. So that first one is exactly the same. Now, in the second one, I've got less stock solution and the same total volume. What do I expect to happen to my concentration? Goes down. How much?
About 10%.
20%. About 4/5, right? Oh, yeah. So the way we set that up is the dilution calculation we talked about back on Monday.
Oh, with the M.
Yeah.
M1 equals M2V2.
Right, so we're going to have the molarity of the stock, I'll just call it molarity stock, times the volume of this stock is going to be equal to the molarity, I'll call it nu, times the volume. Yeah, I guess I should say total. So for this calculation, and we're going to repeat this calculation over and over again. But essentially what we get is, for the first one, we get 54.5 is equal to unknown times 50. 50 divided by 50, you get the same thing, right? Then when we go to the second one, all we're going to do is change that 5 to a 4. 4/5 of our original concentration, right? 80% of the original. And then we just repeat that calculation down for each one of them. You don't have to do it like this, though. You can actually, if you do it in Excel, you can do like a cut and paste or a drag and drop, and it'll just repeat your calculation, and it'll go like super quick. That's one of the great things about Excel, is you can do repeated calculations very quickly. Do we have more questions about the prep?
Not the five.
Not the prep?
Really did that in the most complicated way possible, but I still got all the right answers, so it's fine, I guess.
Great.
Yeah.
You have a tendency to do that.
Yeah, I do, yeah.
Okay. Still get the right answers,
Just
but
like
we want
doing
to
things
we want to
silently.
take the. It's like you're going up the mountain and you're just going straight up the cliffside. It's like there's a trail around the cliff too. It's okay. Cliffsides are exciting. Other questions then, if we've got no more prep activity questions.
Yeah, I had one. I have 3 on the homework. So question 13, question 20, and 21.
Okay. Do we have anything? So we've already done some of those, but we can go back to them since you just got here. I just want to make sure that people who've been here for those don't want to, like, don't have other different questions. Okay. In that case, this usually happens in office hours. About the second hour, we kind of start repeating problems because new people show up because they can finally make it. So we can start looking at some of those problems we looked at before. Do we have any other questions before we go back to the homework? Yeah.
For the preparation activity,
Do we just like actually like write the colors?
Yeah, for prep activity 1, it's a very qualitative, just writing down colors.
Okay.
Yeah. Okay, so since we're going to be repeating information, I might be repeating it in a better way, but I'm going to go ahead and stop the office. Actually, it looks like the office hours stopped themselves. Huh. Well, we're going to go ahead and stop that since it's